Okay, well, we're going to measure ground corn samples, and we're looking at the difference between the use of BioEmpruv and then corn that's not being treated with BioEmpruv for changes to Goss's wilt. And so what I'm doing right now, I'm going to use this, which is the Bruker SD3 XRF. And what that means is X-ray fluorescent technology. So we're going to use X-rays, and we're going to energize the atoms in this sample that I'm going to put on there. And this is ground corn kernels. And then we're just going to press it down because we want to take the air out, because this instrument is so sensitive that we'll actually measure the photons of argon in the sample if we don't just sort of try and make it a little tighter and give it a little bit more density. So we just press it down with a spoon. All we've done is ground dried corn in a coffee grinder. And now we're going to measure it, and it's this simple. This instrument is calibrated for food grains for both the micronutrients and the macronutrients. We're going to run the micronutrients right now, and we're running it with a yellow filter. And what the yellow filter does is it's going to filter out the really light photons from the lighter elements on the periodic table, and it's going to concentrate our photons in the heavier elements so that we can look at our trace elements. We're going to analyze this sample for 90 seconds, and at the end of 90 seconds we'll actually have the concentration of trace elements. But these are the elements that we're really interested in this with this filter, and the trace elements are your manganese, your iron, your copper, and your zinc. You will see a little bit of nickel maybe. We can also measure chromium. We can measure cobalt. All of those will come into this particular analysis. And if we want to go beyond and we want to look at lead, or we want to look at some of the toxic metals, then we would use another filter that will really concentrate the photons from our toxic elements, and we'd get a much better read on the toxic elements. And on our table here, we can actually see what we're reading. This is the concentration. We are measuring manganese to zinc. And the manganese actually is negligible. And that's why we're reading a negative number, because it means that we actually don't have enough manganese. We're below the level of detection on the manganese here. Iron, we've got 16 parts per, wow, that's very low, 16 parts per million. Nickel is 2. Copper is 31, 30. And then the zinc is very high at 76 parts per million in this. And this is the non-treated. So this is the one that's not treated with BioEmpruv. This is the one that we actually see the effects of Goss's wilt on this particular corn sample. So let's, now what we're going to do is I'm going to run the exact same one that's been treated with BioEmpruv, and we're going to compare. So let's go back to this. Now we're on our scan. Now what we're going to do is we're going to go into setup, and we're going to go spectrum overlay, and we're going to move A to B. So now the base spectrum, which is the non-treated corn, turns blue. And now we're going to use the exact same sample that is with the BioEmpruv. Now I'll explain too that we use these little films. When we're doing this sampling, we want to use the film because we're trying to protect the detector. The film is it's a nanometer thick film, so that we're not interfering with the photons and the detector. And again, I've pressed down the sample just a little bit to make it a little bit more dense. Now, this sample is our same place. It's the base of the corn cob, and it's the ground corn kernels. And this one has been exposed to BioEmpruv. And now you can see we've got the second spectrum coming up from our sample that's been treated with the BioEmpruv. So this is the red line. So now what we're going to do is just see if they overlap each other. We'll actually see these peaks, and we'll see whether there's concentration differences between the elements that we're actually measuring. These larger peaks that you see here are palladium and rhodium, which are actually part of the X-ray tube inside the tracer. And so we're actually seeing the reflection from them. So we're not measuring that. What we are measuring is we're measuring right in this area right here. And you can see that the reflections are lining up nicely. That's what we want. This tells us that the matrix, the ground corn matrix, is identical when these overlap like this. So that allows us also to make this comparison. So the first thing we notice is we have a lot less zinc in this one. We have the same amount of copper. We have about the same amount of iron. And so now let's just look at them. This is the sample we just did with BioEmpruv. And let's look at the manganese here. So it's below our detection limit and with the untreated, and we have 25 ppm in the treated. We look at the iron, 16 and 13. Well, I'm not sure that we're going to be able to say that that's actually significant. 2.12, nickel is the same. We look at the copper. Copper is slightly lower in our using the BioEmpruv, and the zinc is dramatically lower in using the BioEmpruv. And actually, this is what we normally expect, is somewhere between 30 and 40 for our nutrient density in a good grain sample. This zinc number, that tells us that there's something going dramatically wrong. Okay, so the next sample we're going to do is from the middle of the cob, non-treated corn sample. Patting it down again. Okay, so now once again we can see that the matrix of the two samples that we ran are very similar because we've got the similar reflection pattern. But now we notice that we're dramatically lower on the zinc and we're a bit lower on the iron here. And then let's just look at that. So that's from the base to the middle of the cob. So what that also tells us is we are not moving nutrients up the cob at all. All right, so now if we look, this is our sample that we just run. We actually have manganese now. We have a lot less iron because if we look at our concentrations here, before our manganese was below the detection limit. Now as we move up the cob, it's actually within our detection limit. We're lower on iron, lower on nickel, lower on copper, and we have dramatically lowered the zinc. And this is all helping us understand the nature of this disease and how it is affecting the nutrient quality of our corn. And this is an important thing because if we're thinking about food quality, then we want nutrient-dense food. And these diseases, these plant diseases, are strongly affecting our ability to grow nutrient-dense food and create food that's really good for us. Okay, so now the next thing we're going to do is we're going to run the same sample from the center of the cob. So this particular corn has been treated with the BioEmpruv. We put it over the detector. We press it down with a spoon so we get some density. The beauty of this instrument is that all I've done is grind the corn in a coffee grinder. I have no prep, I have no extraction, I have no time loss. When you go and do this with an ICP or some other instrument that you would use for trace elements, is you would be taking the corn sample, grinding it very fine, and then you'd be digesting it and then extracting it and then running the solution that's being extracted from. So there are a lot of steps to have losses. And not only that, it's taking a few days before you actually can get your results. So now we're getting the results instantaneously. So let's go back and now let's run our next sample here. Now we're running the BioEmpruv sample. So what we see is a similar pattern to the last one. We see that the zinc is lower. We see that everything else is pretty much the same. So now let's compare D to D. Now this is the non-treated D. So this is the middle of the cob. And this is the treated D with BioEmpruv in the middle of the cob. We're looking at the manganese numbers. Okay, manganese in the non-treated is very high. It's pretty much in line with the base. Iron, 13 for our BioEmpruv, 11 and 16. They're about the same for the nickel. Copper, about the same. Zinc, well, actually it's a little bit higher in the beginning, but this is a nice number. This is an optimal number, whereas this is okay. So now what we can see is that when we use the BioEmpruv, we're getting a very even distribution of the elements throughout the cob, whereas when we have the disease in the untreated cobs, we're actually seeing a real difference in the distribution of the nutrients. So in this case, we've got really high zinc at the base, and then we're, less than half of it when we go halfway up. Whereas when we have used the BioEmpruv, we actually get an even distribution of nutrients all the way up the cob. That's the important thing. So we're maintaining that transfer or that translocation of nutrients throughout the cob with the BioEmpruv, where we are not, where we have the Goss's wilt and we're in the untreated. And now we're going to run the same sample that we just finished before. This is our BioEmpruv at the D level. And now you'll see a very different look. Now in this one, with this calibration on the vacuum and using the lower voltage, this is our rhodium peak here. Now the tube itself is made out of rhodium. The reason rhodium was chosen is because most plants don't ever take up rhodium. In fact, rhodium is a very hard element to actually get access to. So it seemed a good idea to make sure we're using rhodium instead of some other element that we might actually want to look at and would be overlapping. Now, again, this is our rhodium peak, so if we want to make sure our matrix is the same, we need to have an overlap on the rhodium peak. But let's look at so this is our potassium, this is our calcium here, sulfur, we've got phosphorus next, and we've got silica down here and aluminum. So now let's go to concentration. We see silicon, phosphorus, sulfur, potassium, and calcium. And this, I remind you, is the BioEmpruv middle of the cob kernels. We're going to move A to B, and our spectrum is going to change color. And now the non-treated D kernels, and I'm going to press it down again. Okay, and we're going to run this next sample. And now you'll see a red line start coming up. This is our non-treated sample, and we're comparing it to our BioEmpruv sample at the D level, or the middle of the cob. So we can see our matrix is fine. We can compare. Now this is interesting because you can see that our non-treated cob from the Goss's wilt is actually lower in almost everything. So it's lower potassium, lower calcium, lower sulfur, lower phosphorus, but actually it looks like it's about the same silicon. So why don't we look now? This is where we're doing our macro elements. So let's just compare. Well, our silicon is actually quite similar. And we look at the phosphorus, and oh my gosh, look at this. 1300 to 303, 1200 sulfur to 700, 3900 potassium to 2200 potassium, and then the calcium, well, calcium is not nearly as affected as all the other elements. You kind of can expect that you'd have increased silicon. You'd have increased silicon because the plant would actually be armoring itself against the disease. So we expect it to take up more silicon, and that actually has nothing to do with the cob, but more to do with the plant itself trying to resist any further infection by anything. So it's armoring in order to protect itself. But when we start to see limits like this, all the nutrients coming down, if this corn is going into the bin and we're using this as food grade corn, this has very limited nutrient value compared to our BioEmpruv corn. And in fact, if we have Goss's wilt in the field, and any disease that really disrupts translocation of nutrients, what we see is these particular cobs are going to totally dilute the grain from fields that has no Goss's wilt or is not experiencing the same diseases that are affecting translocation in the plant. So from a food perspective, I don't want this in the bin. I don't want this in the elevator. I don't want this in food production. I want this in food production. Now we're going to run the BioEmpruv corn from the base or from A position on the cob. So again, we're not naming any of these, even though we know this is iron and manganese. We're actually concentrating on this group, or the lighter elements in this case. We've got the BioEmpruv. This is from the middle of the kernel. This is from the base of the kernel. So let's just compare. We have more silicon at the base, and we expect that. We have actually more phosphorus. We have about the same amount of sulfur. We have a little less potassium, and we actually have more calcium. But we're going to be more armored at the base of the plant anyways. And now we're going to run the non-treated. Now already we can see that our non-treated corn cob, we have matrix is perfect. They reflect perfectly. We have less potassium, we have less calcium, we have sulfur and less phosphorus. And it looks again like we have about the same amount of silicon as our BioEmpruv treated corn. But let's look at our concentration table now. This whole cob, if we look at the numbers here and we compare them, this whole cob of corn is nutrient poor. It's a poor food source. It's poor for animals, it's poor for people. This is much better, and these are the kinds of numbers that we want to see when we're looking at food density. So, better numbers, poorer numbers, the effects of disease on translocation and translocation into the seed head. Now, here's the other thing with that. When a seed is germinating, it needs these nutrients. That's why those nutrients are in the seed, because the seed actually needs them in order to grow a plant. If we were growing this for seed, we now have a problem. These seedlings will lack vigor because they don't have enough nutrient to actually grow a vigorous plant. The other thing about this is that our non-treated plants actually die and stop filling anywhere up to 4 weeks before our treated plants. Any plant that is severely stressed by disease knows that stress and goes immediately into reproductive mode and tries to get as many viable seeds as it can. But it's forcing the issue. So that's another reason why we see this decline in nutrients, because it doesn't have, and because its translocation system, the way it moves the nutrients up into the plant from the roots, it's all blocked up because that fungus, that bacteria, is actually in there. And the thing is, when we get these lesions, not only do we get the one disease, but we'll get other diseases, and the whole system will become blocked. And so it's like we have this block in the tube. So if you think about it like a hose, it's like you've kinked the hose and nothing's going up. Now we'll find some other ways up and some other ways down, but they won't be nearly as good. And when we're forcing the issue, because we're all stressed, we need to reproduce as a plant, it means that we just take what we've got and we put it in there and hope for the best.